Chapter 9 is all about radiation. So I'm going to start by talking about the definition of radiation. And what radiation is this emission of energy, so that's what this means here, energy, in the form of either waves or particles. And we're going to talk about it in Chapter 9 mostly as particles. So we saw in the other videos, and perhaps the PowerPoint talked about alpha particles, beta particles, positron particles, and then gamma waves. So we are addressing a little bit of both, but mostly the particle region. So I just wanted to go over this table and discuss the symbols that represent these particles, what exactly they're emitting, and then their penetration power. So for the symbols, you saw this briefly in a table in the PowerPoints. For alpha, the symbol used is just that little alpha A, so that guy there. For beta, it's represented by the beta symbol, and then with a +1 here, oops, sorry, -1 for beta, and a 0 here. For the positron, it's also represented by the beta symbol, but instead of a -1 in the lower left, we see a +1. So whenever you see this symbol, this is positron because of the positive sign. For the beta particle, you'll see a negative sign here. And last but not least, for gamma, we have the little funky gamma symbol. All right, now let's look at what is being emitted, what type of particle for these first three. Because the gamma, it's a wave, not necessarily a particle, and we don't really discuss that one very much. So we're just going to look at these top three. So for the alpha, what's being emitted, we described it as a helium atom because it has the same number of protons as a helium, so that's why there's a 2 there. And then it has the same mass number as helium. So this is helium with a 2 and a 4. So if you remember, this symbol here, this is very similar to a nuclide symbol, which we talked about in previous chapters. So when we looked at a nuclide symbol before, it was a way of representing an isotope. And that's where radiation comes from. It comes from unstable isotopes. So it makes sense that we would represent these particles in an isotope form. So when we talked about a nuclide symbol, we had the symbol here in the top left corner, we had the mass number, and then the bottom left, the atomic number, or the number of protons, which is the same thing. So this is how we represent an isotope. So when we're representing an alpha particle being emitted, we represent it as helium, and then the mass number of 4, the number of protons of helium, a 2. Okay, so that's where that symbol comes from there. So that's an alpha particle. Now, alpha particles are the largest. They have the highest mass. Okay, so they're also going to be the slowest. So since they're the slowest, their penetration power is going to be very low. You don't need a lot to stop an alpha particle, because that's the thing about radiation, right? Radiation can be scary. You want to try to limit your exposure to radiation. So alpha particles, since they're the slowest, since they're the largest, they're going to have the lowest penetration power. Another thing you can do to try to lower your exposure to radiations is distance. The further away you are from the radiation source, the less exposure you'll have. So that's another way, as well as protecting yourself, whether it be clothing, a lead vest, etc. That will also help lower your exposure. Let's look at the beta particles next. So we see the symbol representing the beta particle there with the -1 in the lower left-hand corner. Now, the reason for this -1 is because when a beta particle is emitted, we have, or losing, I should say, or emitting, essentially an electron. That's what that -1 sign stands for. So this is what we're emitting. And remember, electrons, they don't have a mass at all. All right, so for this one, Since their mass is smaller, okay, their size is smaller, they're going to move faster, and so their penetration power then is going to be medium. Next, let's look at the positron. So the positron is represented by the beta symbol as well, but with a +1 because of positive, positron. So when we are doing a positron emission, what's happening is a proton is being converted into a neutron. So when that happens, you're essentially going to be emitting a positive charge, a proton, since a proton is being transformed into a neutron. So I'm going to put a +1 here and then a 0 up there. So the beta and positron particles, similar size, similar speed, so they're going to have the same penetration power. Okay, so it's also going to be medium for the positron particles. Now, last but not least, looking at the gamma particles represented by this symbol here. Now, we didn't really talk about what exactly is emitted during gamma radiation. What you do need to know, the main thing, is that gamma particles are the smallest. Gamma particles are the fastest and the most dangerous because of that, because their penetration power is going to be very high. Okay, you need a lead vest. You need a lot to stop the gamma particles. A lot of distance, a lot of protection. Okay, these are the dangerous ones of the 4 that we talk about. So next what we're going to look at is I wanted to approach some of the problems you might see in the homework, because I know the homework goes a little more in depth to the chapter itself and the information in the book. So some of the homework questions aren't covered in the PowerPoint, so I did want to show you how to do a few of them. You could look them up in the book as well, but it's nice to see one worked also. So we're going to look at one of the questions in the homework, or similar I should say, asks you to write the nuclear symbol. So this is kind of a review. So nuclear symbol, and then they'll give you an element and then a dash with a number after the element. So this is the part that's review, because what this is one of the representations of an isotope. So before we had 2 ways to represent an isotope. One was with a nuclide symbol, and that's what this is asking. Okay, this is the same as saying nuclide symbol. So they want you to represent this isotope in this format, with the mass number up here and the number of protons here. Well, to do that, you need to know what this means. So carbon, that's the element. So you just need to find carbon on the periodic table and write its symbol where this X is. But what's after the dash? Well, when we represent an isotope this way, we have the element name, in this case carbon, and then after the dash is the mass number. So this number 14 here, that's the mass number that's going to go up in this upper left-hand corner. Now, to write this as a nuclear symbol or a nuclide symbol, okay, these are interchangeable in this case, we're going to take carbon, we find it on the periodic table, it's a big capital C. The mass number is given to us in this form of the isotope, and it's 14. And then for the number of protons, just look at your periodic table. What number is carbon? Okay, carbon is the atomic number of 6. So I would put a 6 there. So this is the nuclear symbol for that isotope of carbon. Now, they might go so far as to ask you next, okay, well, how many protons and how many neutrons? This is also a review, because if you remember from previous chapters, and it's good we're reviewing this with the final coming up, the mass number, this guy here, is equal to the protons plus the neutrons. Protons count as 1, neutrons count as 1. So let me write that up here. So mass number is equal to protons plus neutrons. Okay, so we know the mass number. It's 14. We know the number of protons. It's the same as the atomic number. It's 6. So what we can do here is, using this equation, we have a mass number of 14. We know the protons are 6, and so what we're looking for is the neutrons. So we have this answer. We erase that question mark and put a 6 there. Well, to figure out the number of neutrons, we just need to take the mass number of 14 and subtract out the protons, because whatever's left is going to be the neutrons, because electrons, their mass was so small, it was negligible, so we didn't count it. So we have the neutrons, what is that, 8? That up here, so we have 6 protons, 8 neutrons, add them together, we should get the total mass of 14. Let's look at a few more questions. So in this first one, there's a question mark here for the reactant side of this emission, but it gives us both of the products. So from this, we can not only glean what type of emission it is based off of this particle here, but we can also figure out what the original reactant is going to be. So how do we do that? Well, first off, let's look at the type. So we see this little helium representation. So that means this is an alpha emission. That's an alpha particle, so that tells us that. Okay, well, how do we figure out this guy here? Well, it's kind of similar, right? We see the reactants, we see the products. And just like when we're balancing equations, we're going to do a very similar thing, except for instead of balancing the elements themselves, we're going to balance the numbers. Okay, so what that means is when we add up the number of protons, which is this bottom number, that's going to equal the total protons of this reactant. When we add up the mass numbers of the products added together, that'll be the total mass of the original reactant. Because what's happening is this original reactant is decomposing in a sense. Giving off alpha particles. So when it breaks apart to give off an alpha particle, it's giving up this new product. Okay, so let's see how we do that. So I'm going to start. We're essentially coming up with a nuclide symbol here. So what we're going to see is we're going to figure out what the symbol is based off of the number of protons, and then we're going to write the mass number up here. So it's going to be in this form. So what is the mass number? Well, to figure that out, we add these two numbers together to get the total mass. So 237 plus 4 is going to equal 241. I'm going to put 241 here. Okay, so we're partway there. Now let's look at the protons. 92 plus 2. 92 plus 2 is 94. Now this is the important part, because this 94, the number of protons, that's going to give us what X is. That's going to tell us the identity of this reactant. Because remember, the number of protons tells the identity of the element. If you change the number of protons, you're changing the identity itself. So now we look up number 94 on your periodic table. Now notice this F block that I told you we won't talk about until the end of the semester, now we're talking about it, where the lanthanides and the actinides are. So number 94, I find it here, and it is plutonium with a symbol Pu. So I'm going to erase this X, and I'm going to put a Pu there. So this would be the correct reactant. All right, well, what if we did this in a word form instead? Because that's what this guy's doing down here. It wants us to write a nuclear equation, and that's what this is, nuclear equation, to represent radium-226 decaying to radon-222 plus an alpha particle. A lot of information here. Now, first off, let's remember, these two pieces here, these are representations of isotopes, where we have the element name dash mass number. Okay, so that's all this is element name dash mass number. So what we need to figure out, well, we have the element, we have the mass number, but all we need now is the number of protons. And since we know the element, we can find the number of protons by finding that element on the periodic table. So I'm going to start. we have radium-226 and it's decaying. So what that means is this is our reactant. This is what's going on the left side of the equation, because this is what's going to be decomposing or decaying. Okay, so radium-226. Well, let me find radium on the periodic table. Radium, there it is, number 88. So if you're looking at your periodic table, it's number 88. So the symbol for radium is Ra. So I'm going to write Ra, because remember we want to write it like a nuclide symbol. So since it's number 88, I'm going to put 88 down here. The mass number they gave us, 226. So that's what I'm starting with. When that decays, it's saying the products, what we're getting, is radon-222 and an alpha particle. Well, I'm going to start by just writing the alpha particle. Remember, an alpha particle is that helium, mass of 4, protons of 2. So that's going to be one of my products. The other product, they said, radon-222. So finding radon on the periodic table, radon is a number 86. So it is represented by the symbol Rn. Put 86 down here because that's the number of protons. And then for the mass number, they told us in this representation of that isotope, 222. So this would be your correct nuclear equation to represent radium decomposing into an alpha particle and radon. So it's really just a lot of practice with nuclide symbols. And you can also see, just like up here, if you add the protons, 86 plus 2, it should equal 88, and it does. Same up here, 222 plus 4 equals 226. So that's a double check just to kind of make sure that you did your work correctly. So I wanted to show this next one because it's not alpha, beta, positron. It's not our normal emissions that we've seen in the other problems, but I do want to show that you can still solve it based off of your knowledge of these isotope symbols, these nuclear symbols. So you want to follow the same sort of path, and what that is, you want to make sure that the numbers on the reactant side are equaling the numbers on the product side. Okay, so in order to do that, let's see what we have. So first off, let's just add up and do the mass number on the reactant side, since we know what that is, right? Because here's our question mark. This is what we're trying to figure out. So in order to figure that out, we need to know what we're comparing it to. So when we add the mass number up over here, let me use a different color, we get, these are the mass numbers up here, so 108 plus 14. I know I should be able to do that in my head, but I'm probably going to screw it up, so let me add that quickly on my calculator. And I get 122. Okay, next let's do the number of protons. So these two guys, 47 plus 7 equals 54. So what are we comparing that to? Well, the mass number on this side is question mark, because whatever the mass number is on that, plus, okay, well, let's look at this. Notice there's a mass of 1 with this particular particle. That's what that top number is the mass number. But there's a coefficient of 6 in front of it. So that means there are 6 of these. So 6 times 1 tells me a total mass of 6 from this particle. Now, I know this has a mass of 6. I don't know the mass of the other product, but I do know the mass number. it has to be the same as it is on the reactant side. So let me erase this. My mass number has to be 122 because they have to equal each other. So to figure this out, you just subtract. 122 minus the 6 mass from this particle will give me the mass of my unknown. So 122 minus 6 gives me 116. So my question mark is 116. All right, well, how do I include that when I try to figure out the symbol? Well, remember, we're just going to write a nuclide symbol here. We're going to have an X, mass number up here, and then the number of protons down here. And we just figured out the mass of the unknown, so we have one of the 3 pieces of information we need, and that's 116. Okay, let's figure out the number of protons next. Well, we know that the number of protons has to be 54, the total, with all the particles on the product side, because they have to be the same. So my number of protons, I'm just going to write 54. Number of protons on my unknown, not sure yet. How many protons from this particle? 0. So that means all 54 of these protons comes from the unknown. So number of protons of the unknown is 54. The number of protons tells us what the element is. I just find number 54 on my periodic table, and number 54 is xenon, Xe. So my symbol, well, that's kind of convenient. I'm going to keep the X and add an E. So it's xenon. So this would be the unknown product that they're asking for. So it doesn't necessarily have to be an alpha beta positron emission. You just need to be able to use your knowledge here, making sure that the mass numbers and the number of protons are the same on both sides will help you predict any unknowns that aren't filled in. All right, so now we're going to look at half-lives. So this is something I didn't cover. I covered in the PowerPoints, but I don't think I did any problems on the last video. So let's look at solving this guy. So in order to solve some of these, you'll have to use the equation itself. And this equation is given on that all-inclusive chapters 1 through 9 equation sheet under course content. That's the equation sheet you'll be using for the final exam. More on that to come. So the half-life equation we have M is equal to MO, and then 1/2 in parentheses raised to the nth power. All right, what the heck does all that mean? Okay, so this M, that is the quantity remaining when we're using half-life equation. So quantity remaining. The MO, this guy here, that is the initial. What did we start with? 1/2, that's self-explanatory, it's 0.5, and then raised to the nth power. So that nth power, that's how many half-lives. So the number of half-lives that have elapsed. So we're going to use this to solve this word problem here. So 122 nanogram sample stored for 1.5 days. How much of the sample remains if the half-life is 12 hours? Okay, well, this first piece of information here, this is my initial quantity. That's what I'm starting with. Now, they don't give us anything else, though. Quantity remaining is what we're looking for, right? How much of the sample remains? So this is what we're solving for in the end. So the only other piece of information we need is this n value. How many half-lives have elapsed? Well, it doesn't tell us. It tells us the amount of days that have elapsed, and it tells us what the half-life is, but it doesn't say, oh, after 3 half-lives, after 2 half-lives. So we need to figure out n. first. That's our first goal, is what is N? So to figure out how many half-lives have passed, let's see what they gave us. Well, they gave us 1.5 days passed. So we have 1.5 days. That's what I'm going to be starting with. That's how many days have passed. And we're going to try to figure out how many half-lives happened in those 1.5 days. So how do we do that? Well, let's see. They say 1 half-life is 12 hours. This is actually a conversion factor. Okay, because they're saying 1 half-life is equal to, is 12 hours. So I can use this to get from hours to number of half-lives. So I can use this to get to N. This is essentially N. But I'm not in hours, I'm in days. So in order to use this conversion factor, I need to get from days to hours. So what's a conversion factor that will get you from days to hours? So how many hours are there in one day? Well, one day has 24 hours. That's a conversion factor we just know off the top of our head. So we can use this bottom conversion factor to get from days to hours, then this top one to get from hours to the number of half-lives. So I'm going to start by using this guy. I'm going to put the 1 day portion in the denominator, opposite sides of this horizontal line, canceling out. That's going to put my 24 hours on top. Now if I stop here, I'll know how many hours that sample was in the cabinet. Okay? But I don't want to know just how many hours, I want to know how many half-lives have elapsed. So that's what this second conversion factor is for. This time I'm going to put the hours on the bottom. So 12 hours is the time of a half-life, and then the half-life on top. Hours and hours cancel. So to solve, I'm taking 1.5 times 24, because remember, multiply across, and then divide what's on the bottom, which is 12. So 1.5 times 24 divided by 12, I get 3. So that means 3 half-lives have passed. So my N value, number of half-lives that have elapsed, is 3. So I have my M sub O, I have my N, now I can solve. So let's look at that quickly. Plugging it in, let me erase this to give us a little bit more room. Pause if needed. Now I'm using this equation here, so M is equal to M sub O, my initial quantity was 122. And then we have 1/2 raised to the nth power raised to the third power. So this is essentially 0.5, and then you want to raise it to the third power, and I get 0.125 when I do that, just this part here, and I'm going to multiply that by 122 to figure out the amount left. Looks like 2 sig figs for here. So I get 15. And in this case, quantity remaining, I'm going to use the same units, nanograms. So after 1.5 days, only 15 nanograms of that sample remain.